This is going to be part 3 of the limit series. So limits part 3. Let's see, limits that don't exist. It may seem a little weird from the previous videos that there's some of these that don't exist, but they're not really that uncommon. So let's review the definition first. The definition of a limit is given by as x approaches a, f of x equals L. So if we can put x closer and closer to a and get f of x closer and closer to L, we say that this limit exists. But there are cases where the closer we get x to a doesn't get f of x any closer to L. It normally actually gets it even further away. And whenever it doesn't get any closer and gets further, we say the limit does not exist. So we'll say limits do not exist if making x closer to a puts f of x further from L. So let's go over a few examples, and what we get the results won't be surprising because you already know in advance these won't exist. So example 1, and I thought of these ahead of time, so I'm not making these up off the top of my head. Not sure if I could do examples that don't exist quite that quickly, but they're not too bad to think of. So the first one, we'll be finding the limit as x approaches 4 of 1 divided by x minus 4 squared. Well, let's see, since we're going to x approaches 4, we'll say try x equals 3.9. Well, f of 3.9, so we're just going to plug that in here, is equal to 1 divided by, and we'll put 3.9 here. 3.9 minus 4 is equal to negative 0.1, and that squared is 0.01, and 1 divided by 0.01 equals 100. So it looks like it's going to 100. Looks pretty clear, right? Well, not exactly. We'll try a different number. Try x equals 3.99. Well, f of 3.99 will still have 1 in the numerator, so 1 divided by 3.99 minus 4 is equal to negative 0.01. But if we square that, we get 0.0001. And 1 divided by 0.0001 is equal to 10,000. So clearly, man, I'm not going to write that out. It becomes pretty clear now that the closer we get x to 4, the further we get from any actual number. It just keeps going and getting bigger and bigger. So the limit here does not exist. And it's going to be pretty commonly abbreviated DNE. I'm not sure if that's a widely used thing or just something that I personally do, and that, like, one of my teachers did it, and I thought that's a good way to abbreviate it, so I started doing that. I'm not sure if that's widely used abbreviation, but that's something I'm going to use in a lot of videos. Anyways, example 2 will be the limit as x approaches 3 of 6 minus x squared divided by 6 minus 2x. This right here is a common form of something that you know is going to have a limit that doesn't exist. It's where we get some actual number in the numerator, and we're plugging it in gives a number in the numerator and 0 in the denominator. And you can't divide by 0, so anytime you get a limit where you would essentially be doing that, if there's a number in the numerator, you're normally going to have something that doesn't exist. But let's try it out just to make sure. We'll say f of 2.9. Let's get the calculator out and see what that is. 2.9 squared is 8.41, so 6 minus that gives us negative 2.41 in the numerator. And 6 minus 2 times 2.9 gives us 0.2 in the denominator. So negative 2.41 divided by 0.2 equals negative 12.05. Well, doesn't seem that bad of a number. Let's try getting a little bit closer to 3. F of 2.99. I think that was pretty predictable that I was going to go there. Well, let's see what we get. 2.99 squared is 8.9401, so 6 minus this gives us negative 2.9401 for the numerator. And for the denominator, we get, let's see, 2.99 times 2, 6 minus that gives us 0.02. So if we do the numerator, negative 2.9401 divided by our denominator, we get negative 147.005. So here, as x gets closer and closer to 3, our answer gets closer and closer to negative infinity. If we got closer to 3 from the other side, I'm just going to allude to something we'll go over in the next video, is let's say f of 3.01. I think you'll find this example interesting. Well, 6 minus 3.01 times 3.01 is equal to negative 3.0601. And if we divide that by, let's see, 3.01 times 2, 6 minus that gives us negative 0.02. So negative 3.0601 divided by the denominator, negative 0.02, gives us 153.005. And something we'll go over next video is this is called a one-sided limit, or where the limit as you approach 3 from either the being below 3, the left-hand side, or above 3, the right-hand side, is actually a different thing. Actually, I guess you wouldn't call this a one-sided limit, but it's still interesting to see that if we go from one side of 3, we get large negative numbers, and from the other side, we're getting large positive numbers. So the limit here does not exist. And then we'll go with one more example. Let's do it in teal. So example 3. We'll say the limit as x approaches 0 of cosine of x divided by sine of x. Remember to put your calculators in radian mode. That's important for calculus. You could do calculus in degrees or whatever else is used, but radians are so much more common that unless you're told otherwise, you should assume radians for calculus. Well, let's say f of 0.001. Let's just get right to it. Equals the cosine of 0.001 divided by sine of 0.001. And if I plug that in my calculator, I get, let's see, sine of 0.001. Plugging that into my calculator gives me 999.99 and then some other numbers. So it looks like this could be approaching 1,000, but let's put a different number in there just to make sure. We'll say try f of 0.00001. So we have 4 zeros. So cosine of 0.4 zeros and a 1 divided by sine of 0.4 zeros and a 1. Cosine point. So putting that in my calculator at home, I get 100,000. So the limit, we'll write it mathematically. So limit as x approaches 0 of cosine of x divided by sine of x does not exist. And something interesting about this problem is if we had sine of x over cosine of x with that same limit, it actually would exist. But you can figure out why that is on your own. Yep. We're done with this video for now. For the next time, we're going to be keep messing this up. We're going to be going over one-sided limits.